Good afternoon, everyone. In this video, we will continue our discussion with class design, steps for class design, and we'll be looking at designing algorithms. So, during the designing an algorithm, we have to formulate an algorithm for each and every operation. Okay, we have already identified the operations during the previous video, and we were basically trying to realize these use cases. Okay, so now we have to basically formulate an algorithm for each and every operation. The analysis specification basically tells like what the operation does for the clients. Okay. Whereas like the algorithms actually show like how it is actually done. There are several steps which we may have to follow, okay, in designing these algorithms. So first thing is like we have to choose those algorithms that actually minimize the cost of implementing operations. Okay, reducing cost is always critical. We'll discuss that in detail. Okay, then we have to select the data structures that are appropriate to the algorithms. Then we have to define these new internal classes and operations, okay, as necessary. And then like we have to assign the operations to the appropriate classes. So these are the steps which are to be taken care, and what we do during each and every step, like we'll discuss in the coming slides. So the first step is like choosing the algorithms. Okay, as I already mentioned, like we have to choose the algorithms that actually minimize the implementation operation, minimize the cost of implementing those operations. Okay, when efficiency is not an issue, okay, in your system, okay, we can use very simple algorithms, okay, when the efficiency is not so critical. But typically in any system, like 20% of the operations actually consume approximately 80% of the execution time. So these 20% of operations are pretty much complex. Okay, for the remaining operations, okay, so which are the other 80% of these operations, okay, it is better to have algorithms which are very simple, understandable, and easy to program. Okay, so the design can be simple there. Of course, like for the complex things, okay, those things like which are actually consuming the 80% of execution, if you want to find an algorithm, okay, there are several considerations for choosing the right algorithm among the different choices you have. Let's try to look at them. The first one is definitely computational complexity. Since you have already I assume like all the students are taking data structures course, so you will understand it very pretty straightforward. It is for you. Okay, so computational complexity is very critical. Okay, so basically it tells like how does processor time increases as a function of data structure size. As the input size is increasing, what is happening to the processing time? Okay, so that is what is actually defined in this sort of computational complexity. And there are several types of defining it. Okay, so whether it is constant time, whether it is linear time, or is it quadratic time, or an exponential time. Okay, so if you have an algorithm which is of exponential time, it is really bad. Okay, try to find an algorithm which performs a little bit better in terms of the computational complexity is concerned. So can you find a linear, okay, complexity, or worst case, like at least can you find a quadratic one? Okay, but definitely not an exponential one. In the simplest sorting case, which you might have already studied, okay, the bubble sort takes like order of n squared. Okay, but there are certain efficient sorting mechanisms, something like merge sort on average like takes like order of n log n. Even quick sort also takes order of n log n. Okay, and there are several other algorithms. So you should be able to, I mean, like this is one of the main considerations in choosing an algorithm for that particular problem. Okay, one is computational complexity. Then the next one is like ease of implementation and understandability. Okay. So it is worth giving up some performance on non-critical operations if you can use a simple algorithm. If it is not in that particular 20% of the operations which actually consume a lot of, they are critical and then like it is consuming a lot of execution time, that's a different matter. But if it is not, okay, if it is not so critical application, okay, we don't have to worry about the performance always, and we can use a simple algorithm. Until and unless there is a performance problem for you, it is not worth doing a lot of optimization actually in the source code. Okay, do the optimization to the level which is required, but not like a lot of optimization. if you do a lot of optimization, it actually makes the model very harder to understand. Okay, and at the same time, like it's also very difficult to prop against. Okay, you define complex algorithms in your model. Okay, during the design stage, for the implementation, it will be pretty much complex. Okay, you need to have the right team to be able to implement such a complex algorithm. You can design it. Okay, then like, do you have a team which actually can implement it? Whether it is really understandable, so easy. Okay, these are the considerations for choosing among different algorithms. The other thing which it comes is like the flexibility. Most of the systems, most of the programs, whatever you write will eventually be extended. Okay, or else like the system will die out with time. When you have like a highly optimized algorithm, this as I already mentioned, like this sacrifices ease of change. Okay, so it is difficult to understand, so that means like it also sacrifices ease of change, so it is not so flexible. So you need to find a trade-off. Okay, you need to find a balance. Okay, which algorithm you should be choosing for your particular problem, for your particular operation in the system. Now let us look at the ATM example. Okay, in the ATM example case, okay, so if we really look into that, okay, so the interactions between the consortium computer and the bank computers could be very complex. Okay, because like the considerations which you should be taking is like it is distributed computing. Okay, so basically like the ATMs are lying at different locations, the consortium computer is at a different place, bank computers are at different places. Okay, then like we have the scalability issue for the consortium computer. It need to talk with a lot of ATM machines, and also like it has to talk with a lot of banks. Then again, like the other complexity which comes is like the inevitable. Say for example, all these bank systems are separate applications. Each bank has their own application. Okay, when you are building an ATM system, like you are not also building the bank system. They are very complex on their own. Okay, so that means like each application. Okay, so when this consortium computer has to talk with all these bank systems. Okay, it need to converse with them. Okay, so basically like you need to coordinate across several data formats. Okay, each bank may follow a separate data format. Okay, so that means like you have to, whatever the consortium computer, basically it has to have these inevitable conversations and then like compromises and coordinating these various data formats. So these are all the things like which you have to consider, okay, while finding the right algorithm for that one. Okay, so all these issues actually make the choices of algorithms for coordinating the consortium and bank very important actually. And not just that one, of course, like designing and then like developing those algorithms. Okay, designing the algorithms for this consortium computer is critical. But at the same time, like say for example, even the simple operations which you actually think, something like ATM withdrawal. Okay, even that one may become like a very complex algorithm on its own. Say, for example, a decision to approve or to reject an ATM withdrawal may not be a simple logic as we think. It may be pretty much very elaborate logic. Okay, it may depend on the customer's credit rating. Okay, what is his past activity patterns? Say, for example, like in the past 1 week, like he tried to withdraw money several times. Okay, and it is outside the country. Is there any credit card fraud which is happening there? Okay, so the algorithm should also decide that. Okay, so these algorithms will become like pretty complex on their own. Okay, and then like how much you are trying to draw, whether how much, okay, how much balance he has, okay, how much withdrawal amount he is trying to take, whether he is trying to take all the money which is there. Okay, then what you do, what the withdrawal method should be doing. Okay, so the logic itself is complex. Okay, then the algorithms have to actually deal with all these things. That's about finding the right algorithms. Then we have to find the right data structures as well. Okay, all these algorithms actually require the data structures on which you have to work. Okay, when we are choosing the data structures, we have to choose the data structure which ideally fits for that particular algorithm. Okay, so in that sense, like data structures basically organize the information in a form convenient for the algorithm which you are trying to develop. So many of these data structures are actually instances of container classes. Okay, so they can be like arrays, lists, queues, stacks, okay, sets, or bags, or dictionaries, and then trees, okay, graphs, etc. These are the different type of data structures, okay, which you will be using. And most of the object-oriented languages actually provide several generic data structures, and then their implementations with respect to modifications, etc., as part of their predefined class libraries. The lab, like we have already seen, how we can use the collections, okay, in Java. Say, for example, if you think in terms of where you need such data structures, think in terms of the ATM case, which I have been talking about. If you have a transactions, the transactions should have several updates happening. Okay, we already discussed, okay, during the previous video. So processing a transaction has several of these responsibilities, and then basically it has dealing with a lot of updates. Okay, so then like a transaction actually need to have this sort of ordered list of updates. That's about choosing the right data structures. Then we will also have to define these internal classes and operations. Okay, since you have these new operations, okay, whether you can be able to put them into the current existing classes, or like we may have to invent new and low level operations, okay, and we may have to have like low level classes as well, into which like you are actually placing. Fundamentally, the operations are actually being decomposed, okay, into several sub operations. So the high level operations are being actually decomposed there. Of course, as I already mentioned, like this expansion of these algorithms may actually lead us to create new classes of objects, okay, hold these sort of intermediate results like whatever we will be computing. Most often, like typically, the client description, what we have got originally about the problem, okay. So when we had actually got it from the system conception stage, we not mention these low level classes. Actually, these are all the artifacts which you have identified during the design stages. So let us go back to this ATM example again. The design details from this sort of process transaction use case actually involves a customer receipt. Okay, that is what is actually identified during the design stage when we were looking at this sort of use case relation. Okay, so the ATM actually should post each and every update to a receipt. Until now, the receipt class was not there in the class design, either from this sort of domain analysis or from the application analysis. This was actually identified during the design stage. So we need to add this sort of receipt class, okay. So into this sort of class model, which you are updating as part of this class design step. That's about defining these internal classes and operations. Then you have identified a lot of operations in the design stage. You have actually decomposed a lot of these high level operations, and then now you got a lot of new operations, okay. And of course you already have created certain new classes, but where do you actually put all these operations? When a class is actually meaningful in the real world, the operations on it are also usually clear. So basically when we were thinking in terms of our domain analysis, okay, we were not finding so many operations at that particular time, but even if there is a particular operation which you have identified, it's very easy for you to put it in that particular class. In the domain analysis, we were talking about domain objects, and then the class has real world meanings there. But during the design stage, we have introduced a lot of internal classes. These things do not correspond to real world objects. Then the major question there is how do we actually decide what class owns a particular operation? Where you will put a particular operation, in which of the class? Of course, there are several steps for that one. Let us try to look at it. Okay. When there is only one object which is actually involved in an operation, then the problem is pretty much clear. We can make that object to perform that particular operation. Okay. But the decision becomes very complex, and it is very difficult when more than one object is actually involved in an operation. Let's try to see cases where you may need more than one object to be involved in an operation. For example, okay, so of course the problem itself is when there are more than one object actually involved, okay, in a particular operation, we have to decide which object plays the lead role in that particular operation. Okay. So the point is say for example in a particular operation, if more than one object is actually involved, okay, so then we have to see which object plays the lead role, and then basically take that operation, put it in that particular class. Okay, let me discuss about certain cases where you will actually decide. Okay, where to put that particular operation, in which class you will put. Think about the case of receiver of the action. Okay, you have to ask the question: is one object acted on while the other object actually performs the action? Say, for example, object one is actually the one which is actually performing an action, and the object two is the one which is acted on. Then basically, like, associate the operation with the target of the operation rather than the initiator. So then basically put the operation whatever I was talking in this sort of object 2. That means like you will be putting this operation in the class of object 2. Okay, because that is the one which is actually doing the action. Okay, whereas this object 1 is the one which is actually just initiating that. Okay, then that's about one way of thinking. Okay, one issue. Then say, for example, you can have a query versus an update. Okay, say, for example, one object actually is modified by that operation, while the other objects are only queried for that particular information, whatever you have. Okay, if that is the case which is happening, the object that is actually being changed is the target for that particular operation. Okay, so like that, you have to basically take an operation and then like you have to see like what are the different okay, so within an operation, what are the different objects which are actually involved, and then like you have to ask certain questions, and based on that one, like you have to decide in which of the object you will be putting that particular operation. Then there are also these focal classes. Okay, say for example, if there is an operation, okay, that actually involves a lot of classes, objects, and associations. Okay, when you look at them, okay, and then like if you look at the complete class structure, okay, from those particular classes and associations, and if you go and look at this sort of class model, which class is actually the mostly centrally located? If it is a star topology, which of the class is at the center? Okay, and then like it is better to put that operation in that central class. Okay, these are called the focal classes. And of course, like analogy to the real world, if you can again like put an analogy to the real world, then it is easy for you to put that particular operation in that one. Say for example, whatever, if it is moving or something, if you can like a physical object, like you can have an analogy, you can actually put it there. Okay, this is how like you will be putting which of the operations to which of the classes. Okay, but sometimes it is very difficult to assign an operation to a class. Okay, especially when you are thinking in terms of generalization hierarchy, whether you will put that operation in this sort of superclass or the subclass, that will be again a complex problem. Okay, so it is very difficult to address. And during the design stages and during the iterations, it is very common that these operations actually move up and down in this sort of class hierarchy. It is very common actually, because as you are adjusting the scope, okay, of a particular class, the operation and etc. So these things will basically move across in this sort of generalization hierarchy. But in general, like the definitions of the subclasses are a little bit fluid. Okay, say for example, like the superclasses are a little bit rigid. If you change anything in the superclass, like several of the subclasses are affected. But most often, like if you basically try to change anything in the subclasses, not many classes are actually affected. Okay. So, but of course, as I mentioned, like during the design stage, like so these things, these operations actually move across this hierarchy up and down. Now let us try to look at the same ATM example. Okay. During the earlier video in this sort of use case realization, okay, we have seen like process transaction actually involves several operations: withdrawal, deposit, transfer. We have discussed very clearly at that time, like each of these operations, okay, involve several responsibilities. To remind you again, like say for example, withdrawal actually has a lot of responsibilities. So we have to get the amount from the customer. We have to verify that amount is actually covered by the account's balance, whether you have enough amount or not. We have to verify that the amount is within the bank's policies. Okay, so today like banks will give you only 10,000 rupees, and if the user is trying to ask for 20,000 rupees, okay, so basically that's also has to be verified. Then we have to verify whether the ATM has sufficient funds. Then we have to disperse the money, and then like we have to debit the bank account. Okay, and then we have to post the entry on the customer's receipt. Okay, and then like we also have discussed like database transactions ensures all or nothing behavior. Now if we have all these responsibilities, these are the ones which are actually becoming like these operations file, and these are the operations which you are trying to put them into respective classes. Now if you really look at them, okay, say for example in this example, get the account will go into the customer class. Okay, get amount will go into the customer class. Verify the amount, okay, and whatever the amount is giving, so this will go into several classes actually. Okay, so it will go into the account, it will go to the bank. Okay, it will also go to the ATM, because the ATM should have enough money. Okay, so it is going into several of these classes. Okay, this particular operation. Then you have this disburse fund will go into the ATM class. Okay, and then like this debit the amount will go into this sort of account class, and post the transaction will go into the receipt class, and the receiving funds will go into the ATM class. So in this sense, like a single transaction eventually, okay, which is part of one use case, while realizing you have identified several operations, the operations themselves will have a lot of responsibilities and all the sub operations which you have designed. Okay, and during this sort of class design stage, okay, of finding the right algorithms, okay, and choosing those particular right methods and putting them into the classes. Okay, that's how like you will find so many algorithms, so many operations, and you are actually putting them into those respective classes. So that's about the discussion. Okay, and regarding the references are concerned, okay, so we are still in chapter 15 of this object-oriented modeling and design with UML. Michael Blaha and James Romberg. Thank you very much for your attention.